Sarath, you can start the you can give the summary of that week too.
Yes, sir.
Yeah.
So can you please raise your hands? How many of you have completed week 1 before starting the session? Okay, how many of you have completed week 2 as well? Okay, in this week I will just cover a basic fine. In this week, I'll just cover the basic overview of the computer networks on the top mark, on the top level. And in the upcoming weeks, in the next week, I'm gonna start the application layer. So this week will be about the basic overview about how computers will interact and what we need to know, basic things. And I'll just add some of my experiences. What is more benefit, all these things. Okay, I hope my screen is visible. Is it?
Yeah, it's visible. You can start.
Yes. So, do you know how do computers talk to each other? Basically, this question goes to back in the 1940s when the computers get to, rightly even before the computers get to properly make them what we know as a computer, even before in the 1940s at the time, where it was just a mechanical systems, kind of those things. At the time itself, there is this question: how do they want how to make it two computers or two systems to talk to each other? Does anyone know how do we make, if you want, in a basic? Okay, so for basic two computers, what you can just do means either you can use a Ethernet cable to make them talk by using a RJ45 cable, or else nowadays we can even use the Wi-Fi. We can make a connection between a mobile and laptop or two mobiles or something, anything like that, using the uh, Wi-Fi. Wi-Fi is actually, actually there is nothing like, actually the name Wi-Fi is not actually a proper name. It was just for our convenience we are using. The actual Wi-Fi name, what we turn on the Wi-Fi, right? It is called 802.11. That is the technical name. For our easy conveniences, for easiness of humans, we use the Wi-Fi, the word Wi-Fi. So two computers gonna talk with the Ethernet cable, and this is the RJ pathway. And just a quick, interesting question. Do you know if for suppose there is a Wi-Fi router, a hotspot, for example, a Wi-Fi router or hotspot, anything. Nowadays, all those things are becoming can be make in a single device itself. So whether a Wi-Fi or this Ethernet cable, which one will be more fast? If both, which one will be more will give us the best speed? If the both are having a same speed, like in the sense of 5 Mbps, and you have connected a device with either with Wi-Fi or with the LAN cable, which one would be the more fast? Anyone of you? Okay. So the fastness will compared to the Wi-Fi in the air medium. Instead of air medium, this cable will produce more speed because there is no, you know, there is no vacuum, there is no space or something like that. Since this is just a electric cable, it will just pass the electrons as fast as possible. Yeah. Now, if you want to make three or more computers talk to talk among them. How do we gonna make it? Does anyone know? We can use a hub. Okay, and but there is some problem with the hub. Does anyone know what is the problem with the hub? Okay, a hub is a you know, one level down, like down in the sense it is not intelligent as the switch. The difference between a hub and switch is nothing but whenever you send a message like hello into the hub here, for example, a computer has a host has sent some message to the hub, something like a print or something. Whenever a hub receives, it's gonna send it to the it gonna do the broadcast. It's gonna send to the all the devices which are connected to it. This is the problem, because at any time only one person can talk, only one person can send a message, and all the others should be quiet. Okay. It's gonna- So what about groups? I'm talking about groups. For example, there is a two computers left here. Two computers are connected, and this is one group. And here three computers are connected and talking to each other. And here one more 4 or 5 computers, group of computers are talking to among themselves. Now, how do we make the group, you know, communicate between each other? Does anyone know what is the best solution for this? Okay, a router. Basically, here, as you can see, this is a one LAN. And does anyone know what is a LAN? When do we use LAN, or what is LAN? LAN is a local area network. It is a local area network. And when do we say a network is a LAN? For example, if it is a building with around 1,000, around maximum of max, I cannot say maximum. It is a building consisting of around 1,000 or 2,000 devices connected among themselves. Then you can say it as a LAN, local area network. Okay, and there is even a lower level called PAN, personal area network, where it's just a router and 4 or 5 devices. Like even your mobile can also become a PAN, personal area network. When you turn on your hotspot, you can give the connection to 4 or 5 devices. So here is a group of computers. This is called LAN 1 example. And here is another group of computers. This is called LAN 2. And if you want to make to talk to the other group, third group, so what you can do means all these devices are connected via switch, as I said, switch or hub, and all the switches are also once again connected to the router. Now this router, whatever, if you're gonna send a message from here, a message gonna come to the switch, and now switch will do the check. Is it internal? If it is internal, then it's just gonna send it to the, whether it is printer, server, or client. If not, then it will just gonna pass it to the above level, so that the next hop. Now this router gonna decide whether it needs to go to the internet, like internet in the sense a large domain, or else should I send it to the it will just, it knows the parts. It depends. I mean, it does, a router does the packet switching based on the uh, IP address range, whatever it was configured. So if it is available in the interface, then it's gonna transfer it to the port. Port is here nothing but an interface. In logical, like whenever we talk in the logical way of logical, it is imaginary, like without touching. It is called an interface. We call it as an interface. But whenever you're gonna see the hardware part, then it is called a port. This is where you're gonna insert a cable or something, that is called in the hardware level, it is called port. Whereas when you talk about in the theory level, it is called interface. Okay. So if it is needed, then it's gonna send it to the next interface, or if it is not related to the internal interface, then it's going to send it to the outside world. Now, once it gets the message, then it's going to come to the router once again, the following router, and it's going to transfer back to the client in the same, approximately same path. I cannot say exact same path because some on the way, some routers might, some devices or routers may go down, up or down, and there are even there are network congestions are possible. Even there are a lot of other reasons. So this is just a basic top level. So let us get, are there any doubts until now? Hello. If not, let us get into some history. So as I said, right, this is from the late, around the World War time. So actually the internet was first developed in the DARPA, Defense Advanced Research Projects Agency. It is the Bell Laboratory. I mean, under the DARPA, there is even a Bell Laboratory. I hope, does anyone bring this Bell Laboratory, where the C programming, where the top-notch research innovations are being done. Okay. So in the DARPA, Defense Advanced Research Project Agency, at the time, it is trying to create a network so that they will be able to make the devices talk to each other and make a network. So this model is called DoD 4-layer model. DoD is for Department of Defense 4-layer model, and it was developed in the 1970s for the DARPA Internet Network project that eventually grew into the internet. Actually, this was a DARPA project was actually in the following time. It was a closed project, and at the same time there are other universities and other IBM, other research groups, Xerox. All those groups are working at the same time to create this networking. So each one of them have created their internal network so that they will make the one device talk to each other. Internal routing can be happening between those devices. So, and eventually this DARPA also made it open source, the internet. So in the DoD, there are 4-layer model. This is the network access layer, where the below, like a physical layer, will come to these things, physical layer, data link layer, in the next upcoming slides or in the upcoming weeks. This is the network access layer, where whenever you're gonna send a message, right? It's gonna put in which will be turned into cable, like a bits and frames will be in this layer, and this is the internet layer. This is the middle. Right now, it is a middle layer, if you ask me. Here, the routing will happen, like not routing. In the host system, what is the whether based on depending on the IP address, depending on the IP address, the transfer will be happens. And here is the host. Here host will make that whether the packet has reached or not, the sending or transferring, the connection starts from here. And this is the application, whether it can be Firefox or Chrome or any other browser. So now this DoD 4-layer model is as I said right previously, there are DARPA and IBM and Sun Group. All those groups are making their networks, and so they made it open source. And after some time, the European standards came into the play. ISO, this is called OSI 7-layer model. OSI full form is Open Systems Interconnection, and ISO is the International Standards Organization. At the time, they had brought this to make it standards. They made this following, as you can see. So the network access layer is separated into 2 layers. One is physical and a data link. The physical layer, where it is nothing but a cable. You can think of it as whatever the cable medium. It can be a normal cable or fiber optics or coaxial cable, twisted pair. Data link, where all this data link and physical layer, those 2 things are implemented in the NIC card network. network card, network interface card. Okay, and this is the network layer where this will be implemented in the sense here here is the part where the IP address will be attached, and all the below three layers, network, data link, and physical. These three layers will be available in the intermediate nodes. Like not every device, most of the devices like routers. Yeah, routers will mostly have these three layers. Why not the above means? Why not the above means? The above the above full stack will be available only in the end systems where the two services are talking. The transport layer, it is implemented in the kernel, where this whether it can be TCP, IP, or else it can be the more. In the next upcoming weeks, we're gonna learn a lot of TCP algorithms like a TCP Reno and ARQ. So there are a lot of few more algorithms. There are a lot of other algorithms. All those protocols will be implemented in the transport layer. Here is the kernel, and the above layer. This is the application layer, and these presentation and session. These are about like whether it depends on these can be implemented or can be not. It depends on the developer, network application developer. It depends on it depends on them whether to implement or not, or they can just skip this below two layers like a presentation and session and jump right away to the application. Okay, so what are the each layer details and the functions? That's it. An application layer, you can consider an application layer as simple as our Firefox. This is an application, and here the connection will gonna happen. And yeah, the application can use the different protocols. Okay, network applications such as file transfer, that is the FTP, and terminal emulation, all those things. As I said, the POP, post office protocol, POP. This is the protocol which is used in the emails, and there is SNMP, simple network mail protocol. These are some protocols, and all these are the best thing about this the internet is these layers. These layers are in the format of layers. So whatever you're gonna do, you can do it in you just gonna do it in the part. You can update or make some changes. Still, it will not affect the whole internet. So it will not affect the below layers. You can just update, and the below layers are just gonna need a message. Like it's kind of a parcel. Here, for example, we say a hello message, and this hello message will be taken to the presentation, and it will nothing but you imagine it as a box of parcel. Once has been packed, and a label has been attached, and this label, only the label details are needed for the session. Now once again, the session layer we're gonna take the box, and it just checks it, and once again it add one more layer of protection, kind of one more layer. It's gonna once again wrap it. So all those things gonna wrap it at the same time. I mean, not at the same time, in the same way. Session layer we're gonna do add some extra data and wrap it, and transport layer also. Transport layer here also it will implement like a sequence numbers, all those things, and it gonna sequence number and whether which packet is the right order, and this kind of information will be attached to it and wrap it and send it to the below layer. Now below layer doesn't bother what is inside the packet. It just cares about a packet is arrived, and I'll just it focuses only on its job. Now network layer will what it gonna do? It's just gonna just wrap it on the after wrapping the package. It's just gonna add the IP address and the source address and destination address. These things, and similarly the following below layers. And once the physical layer, it's nothing but bits and pieces, zeros and ones, or you can say electric pulses. So once again, I will go through it. As I said, application layer, it is just network application layer, whether it can be any email applications. And presentation, as you can see here, the function it does. It is not always just a single function. It is a interrelated. Both the layers will need to be interact. As you can see, this one application and presentation does the half job, half of it. This kind of interplay will happen. They need to communicate with each other properly. For communication, we use protocols. Okay. And presentation and session. The raw message will be taken, and once it is taken, it will be data will be formatting and encryption. Like why? Because we're gonna need formatting. The internet is fully congested. Whenever you're gonna send some packet, right, like a data, it is usually by default it is compressed using gzip. Okay. And there is this session layer. This is the session and transport, establishment with connection, and the maintenance of sessions. Like if you open a new tab and make a connection with the SP or some other banking application, it keeps the session, and only to that browser, only to that in that browser, only in that certain web page only will get access of certain information, not the other side. Other windows are not gonna get access to the data. So this will be implemented in way. And transport layer, this is the main layer. This is the one there are a lot of algorithms are there. We're gonna mostly discuss. Okay, as I said, and provision for end-to-end. Yeah, transport layer will make the end-to-end reliability, and it will here in this layer only we're gonna have two ways, whether we can send the data in a reliable way and the other one is unreliable way. When you are making reliable way, reliability will takes time and a lot of queuing and a delay will happen. Unreliable, it's just we are just gonna send the data. We don't care whether the data has reached or not. We're just gonna send it. If it doesn't reach, the once again in some we're gonna get a message like we have not the other host system will say I have not received a certain packet. So once again the the UDP protocol once again it's gonna send. So coming to the reliability, for reliable protocol, reliability, there is this TCP protocol which gonna give the reliability, and for unreliability there is this UDP protocol. These are the two main protocols. In this main protocol there are multiple algorithms too. And nowadays, previously, very at the beginning of the, until like around 2000, 2010, TCP has been in the main backbone protocol, you can say, for the reliability on all those things, for the most of the internet layer, all those things. Nowadays, even there is this Google layer, Google protocol. Does anyone know what is this protocol? QUIC. QUIC. QUIC is a protocol. It is developed by Google. So what it's gonna do is it doesn't focus on the focus on the reliability, packet reliability in the middle layer. It will be the reliability will be applicable on the above one layer. It just takes the data and it's the application will check whether the data is received or not. If not, once again it will just give a signal, or it's just gonna send a native technology kind of thing. And network layer, as I said, this is where the IP address gonna be attached and where it needs to be, how it needs to be routed, all those things. The delivery of packets of information, which includes routing information, and a data link layer. Here in the NIC network interface card, we're gonna make it into chunks and receive the data in the fast forward and keep it in the buffer, in the NIC buffer, and send it to the above layer. These things gonna happen. Transfer of units of information, framing and error checking, and physically it is nothing but a cable. You can say cable or Wi-Fi or signal, all those things. So in each layer, data is called in multiple ways. Like for example, a single message is called a different way in different product in different layer. In this application layer, we call the data unit as just as a message. Okay, and in the transport layer, we call it as a datagram. In the transport layer, we call it as a datagram, and in the network layer, we call it as a packet. Yeah, packet. Once again, I'm saying this. In the application layer, a single message, like for example, there is this word called hello. Okay, hello is the message. Hello is the message in the application layer. And when the same message has come down to the transport layer, now transport layer will make call it as a datagram. It is called as a datagram in the transport layer. And similar way, when it comes to the down network layer, it is called packet. And when it comes to the data link layer, it is called frames of data. You can say frames. Usually we call it as frames. And in the physical layer, it is nothing but pulses, zeros and ones, electric pulses or electrons, zeros and ones. Okay, it is imagine like water. We call water in different languages as a different words, right? In English, we say it as water. In Hindi, we say it as pani. Like this. In Tamil, we say it as tani. Telugu is water. Sorry, Nilu. Like this. And the network management and control. These are the cross layer protocols. Some of them are cross layer, and some of them will work only in this particular layer. As I said, for example, of application layer protocols, there is this HTTP, hypertext transfer protocol, which most of our connections are HTTP and HTTPS. HTTPS is nothing but encrypted version of the following HTTP protocol. And there's this FTP, file transfer protocol. This is also unencrypted. The encrypted version is SFTP, secure file transfer protocol. Or there is this even this protocol is implemented using where the protocol is used means SFTP. In the SCP command in the Linux, whenever you are doing SCP, right, secure copy SCP, that command is using this protocol. And simple mail transfer protocol. And there is this DNS. I will come to the DNS in the next part. And as I said, in the transport layer, there is mainly two protocols: transmission control protocol, UDP, user datagram protocol, and RTP, real-time communication protocol is there. But it is not mostly used. Most of the we're gonna learn most in the internet. Most of the protocols which are used in the transport layer is these two: TCP and UDP. And SNMP, simple network management protocol. This is a cross-layer protocol. It works in the transport and as well as in the network. And in the network layer, as I said, IP version 4 and IP version 6, and MPLS, I don't know. So these are the protocols which will be used in the network layer. And there are this ARP and DHCP. ARP is the address resolution protocol. Whenever you turn on your Wi-Fi, right, how does the router connect to this your mobile, or else your mobile gonna connect to the router? What we're gonna do means your mobile, whenever the router gonna send the broadcast the messages. So once this message is gonna come, gonna transfer, right? We're gonna turn on. With our device, with our mobile, we're gonna turn on the hot Wi-Fi, and whenever we connect to that, whenever we try to click on that certain connection, what is gonna happen means our IP, our MAC address. MAC address is physical layer address. That physical layer address will be sent to that certain router and say that I'm connecting to you, and this is your password for this connection of this network. So basically, as password we enter, and once this is done, so here there is this address resolution protocol. Now, whenever a message has been come from the outer internet to the router, now how does the router know? to which device, like if there are 4 or 5 devices are connected, and how does it know to which device it needs to send? It uses the address resolution protocol. Once this packet gonna receive, once the packet has been received by the router, now the router will check with the IP address. It will check the MAC address to which device I need to send this. So it's gonna send the packet to the respective device using the MAC address. And DHCP, the same one of whenever you connect to a network, right? You're gonna get assigned. You will get assigned an IP address. So this IP address will be allocated by this DHCP protocol. And nowadays there are a lot of good implementations. Like once you gonna connect, right, using your hardware device, hardware address. With this hardware address, the IP address will be allocated to you. Like for example, 24 hours or 48 hours. Those kind of systems are also available. Like whenever you gonna connect to the router, every time you wanna get the same IP address, not a different IP address, same IP address for the next 24 hours or 48 hours. How much is the time? Based on the network admin who gonna set those things. Okay, and data link layer. In the data link layer, this is the where, as I said, right, NIC card network interface. NIC card gonna come into the picture. Here there is this Ethernet, and there is Ethernet and Wi-Fi are gonna work for our normal devices, if you ask me, like computer and computer, mobile, all those things. But nowadays, the high performance computing systems are there. The servers, they are not, the data is flowing with the Gbps speed, but the Ethernets and those are not readily, those Ethernet is not good enough for the high performance computing because of this latest demand for the AI and all those things. Data has been moved here and there every time. So because of this network only, even though the servers are having like a huge 2 TB of RAM and like a 96 processors are internally CPU processors are like 96. Even though their system has good enough resource, but still the network will be one of the choking point. It is the bottleneck point where you can't transfer more data. Then there is this something called like InfiniBand. Okay, it is a new technology created for this data. I will just go through this. InfiniBand. This is used in the high performance computing. InfiniBand is, as I said, InfiniBand is a computer networking standard used in high performance computing that features very high throughput and very low latency. Latency is like maybe we'll in the next class we're gonna talk about all this terminologies, throughput and latency. At the time I will explain it. It is used for data interconnect both among and within computers. InfiniBand is also used as either direct or switched interconnect between servers. So it is this is a new technology has been developed for the based on the need. Okay. And Ethernet and Wi-Fi and Bluetooth and LTE long-term evolution. Yeah. And here in the physical layer, these are nothing but bits and electric pulses, as I said. So most of the time I have said the protocol, right? So let us discuss what is a protocol. Does anyone know protocols have ever heard a basic protocol, something like that? A protocol is nothing but like a set of agreement agreement made between the both the parties, and they're gonna follow the set of rules. A protocol, as I said, here is a formal definition. Protocol is a controlled sequence of messages that is exchanged between two or more systems to accomplish a given task. For example, whenever we make a call, right, we won't directly say the message. Whenever we make a call, first we will wait for the receiver to pick up the call. So once he has picked up the call, then we're gonna just say hello. So that what this hello means, it is just gonna represent that our voice, are they able to hear it? This is a protocol which we gonna agree. So once the other person gonna say hello, then we're gonna say hi, I am so and so. Then the other party will also say, yeah, I'm here, I know you, and now you're gonna start the communication one after the other. Now once this communication is over, then what we're gonna say, we're gonna say, okay, I'm gonna disconnect the call. So the other person will also say the similar kind of a word. Yeah, okay, I'm gonna disconnect the call. So once this kind of agreements has to be maintained. Without this agreement, if I just randomly make a call and I'm saying random data, then the other person won't have any clue, and they won't make any better data transfer. And if there is any abruptly connections has been, like for example, if I'm talking in the middle and I have disconnected the call without saying anything, like I'm gonna disconnect, my talk is over and I'm gonna disconnect it. So what you're gonna think? It's like the call has been abruptly disconnected. So you're gonna once again the other end of the person will gonna make a multiple times call. He thought that it can be a signal problem or else some issue has happened. So this kind of issues gonna happen if we are not gonna follow the protocol. So this protocol is a critical thing, so that all the parties which are communicating, they will be agree upon certain rules, and they're gonna make a proper good message. Protocol specifications define this sequence together with the format or data transfer between two remote missions, as I said. So here, if we here it is a one host system mission, and here first the message is gonna start from the application layer. For example, let us say a browser, and using from this browser, the data will be sent to the below layer transport. This is the kernel layer, where the kernel will start to make its work. It's gonna take the data and it's gonna chunk into packets. As I said, in the application layer, it is called message, and here it is called datagrams. It's gonna chunk into small pieces. Now, once this pieces has been made, it will just assign. It will know. It will just keep a track. What is the sequence I need to, which need to be sent first? Like if we are not gonna have the proper start and end. If you are not going to have this proper start and end to your data, and it was sent in a random way, then the receiver won't be able to make good sense out of it. Okay, right? So we need to make sure first packet has to be sent, second packet, and if there is any a packet has been lost, then once again we need to send the packet back. So those following things will be taken care in the transport layer. Okay, and as I said, in the network layer, here the following part where the IP address and all the information will be given. Some checksum protocols, all those will be implemented here. And the data link layer, this is the layer where the same, it will be converted into frames. Here it will be electronically, it was a logical data. This logical data will be once again sent into here, and this logical data we're going to add some message, and here now we're going to break it into chunks so that the physical layer will be able to transfer it properly. Okay, now for example, here the data has been received to this switch, and how do you come into the basic differentiation between switch and this router? Whenever you see a square box, right? Square box and with the following symbols, this is called a switch. And a router usually will have the circle shape, but here it is fine. It's not a mandatory to have a circle. Usually you will get a circle for the router, and with these 4 symbols crossing each other, like directing in different directions. This is for the router. So the switch gonna take the data, it's gonna assemble it. Now once it's gonna assemble it, it's gonna just it's gonna take it. What it's gonna do means it just receive the pulses, electrical pulses, zeros and bits and ones, all those things. it's gonna take it into the data and it's gonna combine it. And once again, it will just check the with respect to the, as I said right here, previously NIC card, network interface card will check only the MAC address. Is it whether should I send it to the internal internal group, or should I send it to the outside? If this internal group, then it will just see and port it to the right interface. If it is not, then it will just gonna send it to the outside where there is a where the more internet or the certain IP range is present. So it's gonna go in the following way. Now this is a router. Now router will take the same process. It's gonna take in the electrons and join it, and here the NIC card will do the same joining, and after joining the above layer, network layer, only in the router the network layer will be present. Now this router, what it's gonna do is once the this electrons are joined and bits are zeros and ones are joined, now it's gonna get some clear message on using from the packets. On the packets, it's gonna check the IP address. Here the IP address will it can be able to see. So in the next session, I will show you a demo of the following transfer of the data, and I will stop at each layer, and at each layer what is the kind of information we will see and all those kind of things. And here it's gonna stop it, and it's gonna check the IP address and source and destination address. So it's gonna check from which source it came and to which destination I need to port it. So once it figured out, so it will send it to the ports. There will be multiple ports will be there in a router, whether which port I need to send it. So once it has figured out to which port I need to send it, then it's gonna once again do the packet, will be sent it to the network interface card. Network interface card will once again chunk that data into like frames and send it to you as a alphabet pulses. And same thing goes here. And now once again, when the end host received it, the end host directly won't decode the message. What it's gonna do is only the physical layer message will be only given to the physical layer. Now this once data is collected, and the following above layer, it just gonna keep the data and check whether it is properly assigned. Once this assignment is done, it's just gonna send to the above layer. The network interface card will gonna make it accurately join the data and send it to the above layer, network layer. So now the network layer is gonna see from which source it came and which destination it came, from source, from where it came, and to which device it needs to go. Now once it checks, it comes from, so for example here it is called A and here it is called B. Also maybe I'll say here from the Delhi to Chennai. So here a message has been sent here on a consider it as a postal. On the postal address, here we have written from the Chennai to the Delhi, from the Delhi to the Chennai certain address. For example, IIT Madras itself. So once a post office has been reached, here this is a post office, and here these are intermediate post office. You can imagine the following layouts and logic. Once it has been received, it just checks whether is it the correct one. Is it the correct post office? Is it the destination IP is correct or not? Yeah, it is to me only, to this destination only, to this destination IP only. So then now the following packet will be sent to the above transport layer. Now transport layer will just make sure the packets has been received in the order, right order. Like if there are 10 packets has to be received, if one certain packet like in the middle like a 4 or 6 or something, packet number 4 or packet number 6 has been lost, then it will know, it will send a once again message to the to this source. It will send a message to the host, this other host, so that once again the host will create the same packet data and send it to the following destination. Once all the packets has been received, now this 10 packets will be like 10 packets is the main data, for example, and this 10 packets will be sent about to the application layer. Now application application layer will do its job and arrange the parts, and once again the compression will be undone and neatly will be rendered by whether if there is a need for rendering or something like that, the application layer will take care. Okay. So as I said, once again, the same thing, the data packet and encapsulation. Upper layers, it will be sent to the TCP transport layer. This is the main message. Upper layer application data. To this upper layer application data, we add a header. It's like a stamp, like above a label. We're gonna on the parcel a box. We're gonna attach a sticker and we're gonna write some information to which it's to go where to where. Similarly here also, all the thing what you need to consider is here IP layer doesn't bother about TCP layer or layer 2. It only cares about it can only decode the IP address, IP layer header only. It cannot decode or encode the above or below layer. It can only make sense of its current same layer level. Okay. And here, as I said, the data will be labeled with the upper level layer data, and the same message, like this box is there, right? You can see this box. This box data will be sent to the below layer. The kernel will what the kernel gonna do means it's gonna just take this data and apply the header, TCP UDP header, so that it will know this is the sequence number 1, this is the sequence number 2, 3. So and now this whole data will be chunked into certain parts. Now this certain chunk parts will be sent to the network layer. Now in the network layer, it will just assign the IP address where it needs to go. The same data. What you need to notice is this data is sent exactly as to the below. Now to this data, we are just adding a one layer of top. Adding a one top layer so that the other person will know where it needs to go. Okay, and here we have added one data, and the same length of this data will be sent to the below layer. And in the layer 2, as you can see, layer 2 header is added and footer also added. Footer in the sense for this is whether it is the checksum, like a write bits are whether if it is the message is 6, for example, it is a 6 in the binary form, 0110, and if the message has been changed it to like 1110, then it knows whether the bits are in the correct form or not. There is some checksums which you're gonna see in the next week. And here there is this layer 1, and it will just convert into pieces. It can be converted into a radio form, like our Wi-Fi radio waves, or else in the electronic zeros and ones. And this will be sent in the following way. And the same way, once this electrons zeros and ones has been received by layer 1, it will just attach join these zeros and ones and send it to the above layer. Now above layer will check will tear down this check the header and footer and tear down this above and below stick labels and send it to only the above part, only from here to here to the above part. Now this once again the IP layer will check the data whether it is to be or not. Once this is done, now it will just tear down this above part. IP header is there, right? It will tear down and it will send it to the above layer, as you can see here. It's gonna go in the similar way. Now once the upper layer gonna receive it, it's just gonna unencrypt it and check the message. Okay, and what is an IP address? So imagine this IP address is a IP address is a unique address. Maybe I'll first go with the formal textbook definition. An IP address is a unique address that identifies a device on the internet or a local network. IP stands for Internet Protocol, which is the set of rules governing the format of data sent via internet or a local network. The best analogy is a postal network, post letter, and a pin code. Imagine you have written a letter, and that is the data which you needs to be sent it to the from Delhi to Chennai. And what you're gonna do on that letter, we're gonna put it in the postcard. Like it is like a application layer has sent the data to the below layer. Now on the postcard, we're gonna write the message. Or else if you feel like if it is like for example, instead of a simple postal letter, you have sent some delivery, and a delivery person can only has said that you can't send 1,000 like a 100 kgs. So what you're gonna do means you're just gonna chunk it into data. Imagine this is chunkable data, like make it into divide it. So what you're gonna do means you're gonna make that load into like a 5 kg, whether it can be 5 kg, 5 kg, and it varies. It depends on each part size. So it's gonna within the limit only. You just gonna break it and write the address and send it to the next one. So now the postal person will gonna take it to the nearest main postal head branch. Now this postal head branch gonna check where it needs to send. The postal head branch, if this needs to be needs to travel to the other district, then it's gonna just send it to the district only directly via normal. You can think of it as a normal cargo on the normal delivery van. It's gonna send it. If it needs to be travel lot more distance, then it's gonna need to choose the better better mode of transport, like whether it can be flight or else ship or whatever is applicable. Similarly, in the these things gonna same way where if it is in the same district, then it's gonna come from if it is in the same village, then it's just going into the from here a message has been sent to the main just a post office, and this message will be sent. If it is the same village in the district, if it is the same district from village 1 to village 2, then it just gonna transfer from the district office to the sub village only. But if it's need to travel to the other district, then it's gonna come out of that come out of that district and send it gonna travel to the next head office of the other district. From this head office of the other district, then it's gonna send to the village post office. From that village post office, the delivery person will send it. If it is not in the same district, then it needs to be transferred to the other state. Then it's gonna come to the router, and the router will transfer it to the other outside. The same information. Imagine it like take 5 after the session, take 5 minutes, and imagine how the how a postal letter will be transferred from one state to how it will be transferred from district to district, and same village, or it's a 2 different districts, or it's a 2 different states, 2 different countries. Then you will get an idea about it. Yeah, and there are 2 IP versions out there, IP4 and IP6. Okay, and actually this goes into the when the project has been designed. The designer who designed this protocol thought it was just going to be a experiment. It was never went to be a normal experiment gonna go into the public and will be used on the large scale. He just thought it was just a for experiment in the lab, or for certain basic experiment thought, and he created a 4 billion address, around 4 billion address as a 4.3 billion addresses. So this address has been exhausted in the around 2000, I think, not 2000, in the 1990s itself. The IP address 6 has been IP address 4 has been like exhausted. Like other devices are being more and more devices are getting the created, and each device need a IP address. For to tackle this IP address, then there came this classless inter-domain routing, where the private network will come in. Private networking will come into the view. The private network part and NAT we're gonna check it in the upcoming weeks. Okay. Okay. IP6 has been to tackle this IP4 exhaustion. There is this IP6 has been created, and it contains this 340 undecillion, undecillion, I think, 340 trillion addresses. These many addresses are there. Yes, and here is just a few information. It is 32-bit, and here it is a 128-bit, and address format is here 4 octets, whereas here it will be 6. I can't say it is octet. 6 will be there, and here the notation will be max. It will be 24, and here is prefix notations. We'll get to know more about this in the upcoming weeks. These are the notations which are very critical in the internet layer. Yeah, and maybe I'll continue about the DNS in the next session. That's it for today's week.
Okay, thanks, Sarath.
Yeah.
Umia, can you solve the week 2 practice 7 question?
Yeah, sure. Am I audible?
Yeah, audible.
Yeah, okay. Give me a moment. I'm just sharing my screen.
Okay.
Yeah, I have shared my screen. Kindly acknowledge this. My screen is visible. Is it visible?
Yes, ma'am.
Yeah, okay. Okay, so the first question is of there is a network router processes. They have mentioned is 300 packets per second, and on average there are 45 packets in the system. Find the average time that the packet spends in the system. So this question they have given two things. One is the number of processes they are the average number of packets in the system, which is of 45, and they have also mentioned the number of routers can be processed, which is nothing but the array1 route. Okay, so by using which we can solve this? Okay, so using Little's law, we can solve this, right? Is my writings are visible, people? Am I audible?
Madam, you're audible and what you're writing is not visible.
Okay, all right. Give me a moment. Okay, I'm sharing my screen again. All right. So now let me know if my writings are visible.
Madam, you're not sharing your screen, ma'am.
No, it's shared. Okay, give me a moment. Is my writings are visible now?
Yes, madam. Yes, madam. Hello.
Okay, fine. Fine. So coming back to this, so here I have to use the Little's law because they have clearly mentioned that two things are given. One is the packet arrival one and then the average number of packets. So average number of packets is what? L, right? Okay, so we have to find, we know that lambda also, which is nothing but the arrival rate, which is of 300 packets per second. So what we need next? We need the average packet spends, that is W, right? So what is formula for Little's law? L is equal to lambda into W. So here we want to find W. So what we can do is we can use it as W is equal to L by lambda. So here I can use it as 45 divided by 300. So what will be the value? 0.15, right?
Yes, sir.
Yes, 0.151. So I get it as 0.15 seconds. So here, what are the options are given? 150 seconds, 150 ms and 300 ms and 1.5 seconds. So now I have to convert it to a milliseconds, that is ms. So 0.15 second is converted to millisecond means what is the value I'll get? 150 milliseconds. So here the answer will be option B. Is it clear? Then here comes the second question. They have mentioned this a fiber optic link is 45 kilometer long. If the signal propagation speed in the fiber is 2 into 10 to the power of 8 meter per second, and what is the propagation delay for 1 bit to the travel from one end to the another? So first, what are the things we need to find? First, we have to find the propagation delay. So what is the formula of propagation delay? Yes. Which is equal to distance divided by propagation speed, right? Can I be able to recollect this? Alright. So here, what they have mentioned is they have said that distance is given as 45 kilometers. So here we are going to convert it to a meters. Okay. So if I convert it to a meter, what will be the value?
45,000.
Yes. So I have got 45,000 meters. So that is the distance I have got. So then what I have to do, I have to find the propagation speed. But what we have got is the propagation delay is equal to speed. So what is the speed is given? 2 into 10 to the power of 8, right? Okay, so on dividing this, what will be the value we'll get? So it's like
22.5 into 10 to the power minus 6.
yes. So here we can just, if you want it in a simple words, you can just take it as 10 to the power of 3 and 10 to the power of 8. I mean, like if it goes above, it become 10 to the power of minus 8, and you can just do the division process and all. Okay. So 45 divided by 2 will get it as
22.5 into 10 to the power minus
10 to the power of minus 5, right? Okay. So now what they have asked us to convert, they have asked us to convert in the way of
Microsecond.
Yes, we have to convert it to a new seconds, which means we have to take it to the 10 to the power of 6, right? Which means we'll get it as 225. Because mu seconds in the sense of we'll multiply by 10 to the power of 6, right? So I'll get it as 225 mu seconds. So here the answer will be of 225. Is it clear, people?
Yes, ma'am.
Okay, I hope this is clear. So moving ahead with the next question. So what the next question is given us a 1 GB file is split into a 100 bits packets and sent from host A to host B, and the link bandwidth is 1 Gbps and the propagation delay is 1 millisecond. And what time does the last bit of the file reach the host is the question. So what are the things were given here?
Total file size.
Yes, total
Number
file
of-
size is 1 GB.
Number of packets
Okay.
and the bandwidth.
Mm.
The propagation delay. 4 items have been given.
Yes, these things were given. First, what we have to find is number of packets. So to find the number of packets, what we need to do?
1 GB divided by 100.
Exactly.
1 GB is
So for the number of packets, we have to take it as 1 GB divided by 100. So what is the value we'll get? 10 to the power of 7 packets, right? Because this will be like 1 GB is nothing but 1 into 10 to the power of 9. So this will go above and it will become as 10 to the power of 7 packets. Is this thing clear to you all?
okay. So 10 power 3 is kilo, 10 power 6 is mega, 10 power 9 is giga.
Yeah.
Okay, ma'am.
So next is transmission time per packet. So what is the packet size we have got?
100 bytes,
100 bytes. Which means if I convert it to bits, what will happen?
800.
Yes, it will become as a 800 bits. So then what we have to find? We have to find the transmission time is equal to packet size divided by the bandwidth. What is the bandwidth given here?
1 Gbps. 1 gigabyte.
It is to the power of 9, right? So you'll get it as 8 into 10 to the power of minus 7. So if I make it as mu seconds, I can make it as 0.8 mu seconds, right? Is this thing clear?
Okay, ma'am.
Okay, so next what we need to find is transmission of all the packets, right? So for which we have to take this number of packets. What is the number of packets we have got? 10 to the power of 7 packets. And we have got the transmission time per packet, which is 0.8 mu seconds, right? Which has to be multiplied by 10 to the power of 7. So what is the value we'll get? It will become as minus 6. This I can write it as 8 into 10 to the power of 6, right?
8 into 10 power 6. Yeah.
2 seconds. Or else, let me make it simple here.
8 into 8001 will be the answer, I think.
Yeah, 8,000 will be the number of transmission packets.
Time
we'll get.
taken.
And
For
each packet has a propagation delay of
1 millisecond.
yes.
So add
So we are adding 1 to it. So at last we are getting us 8,001. That's it. Is this thing clear to you all? Okay, what is given in the fourth question, people? Yes, what are the things we are given and what we need to find? Okay, what is the packet size is given?
1500 bits.
Yeah, okay. And then what is the transmission rate is given?
At the rate of 2 megabits per second.
Yes. And what is the one-way delay minimum?
10 milliseconds without
Yes.
queuing.
And maximum is of 70 milliseconds. And what is the average is given is 40. So first what we have to do, we have to find the average queuing delay, right? So how to find the average queuing delay? Average delay minus the minimum, right? So what is the average delay? 40 minus 10, which means we'll get it as 30 milliseconds, right? Okay, next what we need to find? We have to find the transmission time for one packet. So for finding the transmission rate of one packet, we have to get packet size divided by the transmission delay, transmission rate, isn't it? That is the transmission time, right? Okay. So what is the packet size here? Yes. Okay, so I'm saying that like transmission packet is 1500 divided by what is the rate of transmission rate? Packet size is 1500 and what is the rate here? Transmission rate is, yes, 2 into 10 to the power of 6. So on dividing this, what is the value we'll get?
7.5.
Yeah, 7.5 and there we have 10 power 2 and 10 power minus 6.
10 power minus.
So we can, yeah, we can take it as 0.75 milliseconds, right? Because that is the same notation we are using it here. Now we have to find the service rate. So service rate is equal to mu is equal to 1 divided by the total one we have found. Okay, so what will be the value we'll get? 0.75 ms. So 1 divided by 75 into 10 to the power of 4, we'll get it as 1.33, right? And we have this bars and all, so we'll get it as 133. I mean 1333.333 goes on, right? This packets per second is the service rate we have got. Then what we need to do, we have to find the average number in Q. So this is the arrival rate we have figured out and we know the second delay also, which is 30. So what we need to do? We have to multiply both, right? Because Little's law is equal to lambda into the W. Okay, so on multiplying, what will we get? 1.33 into 30. We'll get 3.99. So on multiplying, we'll get it as 39.999 we'll get, right? Isn't it, people?
Yes, ma'am.
So approximately we can say it as 40 packets.
Yeah.
So what will be the answer here?
40.
Okay, what is the next question? A communication link with a total bandwidth of 10 Mbps is a time division multiplexed among 5 nodes uniformly. And so they have clearly said that it is number of nodes is 5 and the number of total is 10. So what will be the total bandwidth per node?
2 Mbps.
Yes. So yeah, all the options are of same. The next what we need to find, we have to find the how long will it take for a node to transmit 2 MB of data, assuming the continuous transmission during its time slot. So what is the data size we have got here?
2 MB and 2 Mbps, about 8
That
seconds.
is the bandwidth, right? Bandwidth is 2 into 10 to the power of 6. I mean, like 2 Mbps.
Again, the total is 2 MB of data.
Yes. If
So
I convert it to the bits, what will happen?
8, 2 8 is 16.
16 into 10 to the power of 6 bits, right?
6. Madam, you're writing, it is not visible.
No, I'm not writing.
Okay, okay.
Okay, it's clear that 10 divided by 5 is
5. 2 Mbps is
2
the
Mbps. That is clear.
bandwidth
So
available.
next we are taking is the total data. So total data is equal to the
2
uh,
MB, which is
2
equal to
into 10
8.
power 6. As we are converting it to the bits, we are multiplying it with 8 also. So we'll get it as 16 into
10 power
10
6.
power 6 divided by bandwidth is of 2 into 10 to the power of 6, right?
Yes, madam.
Because that is the bandwidth also we have got. And transmission rate is 2. We are converting it to a total data is of 16. So what will be the value here?
8 seconds.
Yes, we'll get it as 8 seconds. Okay. So what will be the answer here? Option
Second one.
second. And here is the second question. So there are 3 users, U1, U2, U3. They share a link of total 10 Mbps. And their demand is 2, 3 and 5. Assume the time slots are allocated proportionately to their demands. Out of 10 time slots, how many slots are assigned to each other?
Madam, we are studying proportions. Same, it will be there, madam. 2, 3, 5.
Yes,
That's
total demand is of 2 plus 3 plus 5, which is of 10, right?
Yeah. So
See,
first one will be
we
the
have
answer.
10 Mbps total. Okay. And their demand is also equal to the 10, right?
Professor has done this same problem in the lectures, no, ma'am.
So we'll get it in the same way as 2, 3 and 5.
Yeah. First option.
Yeah. If you take us the fraction also, it will be like 2 by 10, 3 by 10 and 5 by 10, which means like 2, 3 and 5 only. So here is the next question. What happens when too many packets arrive at a switch at the same time in the packet switched network?
All switch remote to your space. All packets are dropped immediately. So packet switched. Okay. It is not a router. It is a switch or a router.
Which one?
In this question, packet switched network. Packet
No, it's a
switch.
switch.
Switch only, madam. It's not a router.
Huh.
Switch means it has to drop. No, if switch, how all packets arrive, there it will go. No, it is actually dedicated line. No, switch means.
What happens when too many packets?
All packets are dropped immediately is the answer, ma'am.
All the so only if it is full, when the buffer becomes full, then only all the packets will be dropped. But initially they'll be stored in the queue only.
Yeah, but switch and okay, packet switched.
Okay, so what will happen is when the multiple packets, because they have said that many packets are arriving at the simultaneously. So what will happen? The output port will become busy, right?
Yes.
Okay. So what will happen? The switch will queue all the buffers, all the packets in a buffer. Once the source is available, until once the source is available, it will transmit. Okay.
No, packets are queued in buffer
Until the sources are
resources are available.
Yeah.
Okay. Once
If
the
you-
buffer is filled, then
Then
it
it will just drop it.
drop it.
Here is the last question. In a packet switch network, buffer management is important because of
Yeah, first it prevents packets from being lost during the traffic spikes. No.
yes. Because as we have it's related to the previous question, when it is many packets are arriving even at the same time, it is keeping it in the queue only. Okay. If there is a heavy traffic also, at least it will it will store the temporary, it will store the packets at least temporarily. Okay.
What are the two types of network? One is packet switched and the other one is
Yes.
dedicated. We have no what it is called as that tunnel. Packet switch is one network. What is the other type of network? Hello, can you hear me, ma'am?
Yes.
In the seventh question,
Mm-hmm.
it tells in a packet switch network.
Yeah.
So, what is the other type of network?
It's circuit switch network.
Circuit switch. Circuit switch. So, okay, we should not get switch and router. I was thinking switch means circuit switch. Packet means it is a router. I was thinking. So, packet switch only. It is named as circuit switch and packet switch. Packet switch will have buffer. Circuit switch will not have a buffer.
Huh.
Okay, correct.
Okay. Any other doubts?
No, ma'am. So you started at 8 o'clock, ma'am.
Oh yeah.
Okay, I joined late. That's why.
Okay.
No problem, madam. Week one, it's clear. It's not so difficult. Okay,
So,
I will see the recorded portion.
yeah. Subhendu sir, do you want to discuss anything? Subhendu.
Chair has got suffer.
No, he was active. That's why I'm just checking on him.
I think we can stop the recording.
No, recording is still on.
You can. That's what I'm telling you. Since
Okay.
you're completed.
Okay. I think he has nothing to share. Okay, people. Thank you.
Thank you very much, ma'am. Thank
Yeah,
you.
thank you.
Let's meet next week.
Yeah.
Good night.